For your next class, we're presenting our projects on Monday, right?
No, Monday is review for the final. Wednesday and Friday are presentations.
Okay, Wednesday, Friday. Cool.
Wednesday, Friday.
Oh, my project is almost done. I just need you to look at my Excel spreadsheet. I came up with a better idea.
Cool. Okay, so let's talk about what's on midterm number 2. You should be able to state the definition of a basis. So remember, basis for a, say, vector space or a subspace is a set of vectors let's say that both span, let me say that are linearly independent and span the vector space or subspace. You should be able to state the definition of a basis. Oh, sorry. 4. So you can have a set of vectors that's linearly independent. You could have a set of vectors that span. You could have a set of vectors which are neither. But if they both span and are linearly independent, then it's a basis. So again, remember sort of that analogy for linear independence and spanning that I talked about earlier in the course. Let's say you have some playing cards, you know, ace of spades and whatever. And there are 52 different, of course, playing cards. We'll forget about the jokers for now. If no two of the cards that you're holding are the same, that's like linear independence. And if you have every card in the deck, even if you have multiples, that's spanning. If you both have, you know, no two cards that are the same and you have every card in the deck, you know you have exactly 52 cards and you have a full deck, that's like a basis. Okay, so let's see. How big is every basis of, how many vectors are in every basis of R2? Two, right, exactly. I mean, with lots of different bases of R2, I could pick, you know, the standard basis, 1, 0, and 0, 1, but I could pick any other basis also. Any pair of vectors which are not linearly dependent form a perfectly nice basis for R2. That's a nice basis, this is a nice basis, and so on. And this is not part of the definition, but you should know this. If V1 through Vk is a basis for vector space V, then every vector x in V can be expressed as a linear combination of the basis vectors in exactly one way. This is the main job of a basis. This is why a basis exists. Is to allow us to express all the vectors in the vector space as a linear combination of the basis vectors and do it in a unique way. So the fact that these vectors span, which they do because they're a basis, means that I can express every vector as a linear combination in at least one way. The fact that they're linearly independent means that I can express every vector as a linear combination of those vectors in at most one way. If they're not linearly independent, there might be vectors that I can express in multiple ways, infinitely many ways. If they're not spanning, there might be some vectors I can't express as a linear combination at all. I mean, if they're not spanning, there certainly are vectors that I can't express as a linear combination on the basis of those vectors at all. So this is the main job of a basis. A basis puts a map on the vector space. It takes every vector and turns it into like these C's, which are like coordinates in that basis. That's the main job of a basis. Okay, so you should be able to state the definition. You should know that the dimension of a vector space is just the number of elements in the basis. Dimension of R2 is 2, because any basis for R2 has 2 vectors. The dimension of R3 is 3, because any basis for R3 has 3 vectors. Okay. Let's see. Given a matrix, find a basis for the column space. Find a basis for the null space. Find a basis for the row space. And you should know that the dimension of the row space is going to be the same as the dimension of the column space, because that's the number of pivot columns. So you should know that the dimension of the row space equals the same, is equal to the dimension of the column space. Because both these numbers equal the number of pivot positions. And you should know that the dimension of the null space is equal to the number of free variables. In other words, it's equal to the number of columns with no pivot position. Oh, we gave the dimension of the row space and the dimension of the column space, we gave that a name. We called that the rank of A. The rank of A is the dimension of the row space. It's also the dimension of the column space because they're exactly the same. It's just the number of pivot positions.
What is it called?
The rank?
Rake?
R-A-N-K.
Oh, rank.
Rank. The rank of A is just the dimension of the row space or the dimension of the column space. It's just the number of pivot positions. Just row reduce and look for the pivot positions to go 1, 2, 3, however many there are, and that's all there is to it. So if the rank of A is the number of pivot positions, it's the number of columns with pivot positions, and the dimension of the null space of A is the number of columns without pivot positions. If you add them up, you get the total number of columns. So the rank of A, the number of columns with pivot positions, plus the dimension of the null space of A, the number of columns without pivot positions, the number of columns with pivot positions, plus the number of columns without pivot positions equals the total number of columns in the matrix. given a square matrix, so n by n matrix A, be able to find the eigenvalues. For each eigenvalue, be able to find a basis for the eigenspace. And then we did a little bit with finding eigenvalues and eigenvectors for linear transformations that I don't give to you like a matrix. For example, that derivative operator we saw that d of e to the x, derivative of e to the x is just 1 times e to the x. And so 1 is an eigenvalue and e to the x is an eigenvector. We saw that the derivative of e to the 2x is 2 times e to the 2x. So e to the 2x is an eigenvalue, 2 is an eigenvector, and so on. In fact, any number is an eigenvalue for the D operator. For an n by n square matrix, you know that an n by n square matrix has at most n different eigenvalues. The characteristic polynomial is going to be an nth degree polynomial. An nth degree polynomial can't have more than n roots. So for square matrices, you only have a finite number of eigenvalues. Something like this, operating on an infinite dimensional space, can have infinitely many eigenvalues. That's it. So computing eigenvalues and eigenvectors, finding a basis for the row space, the null space, the column space, knowing what a basis is, knowing what rank is. This is the crux of the midterm. There's not going to be anything on dot product or inner product on that second midterm. We'll save that for the final exam along with the rest of the course. What are your questions? Is there anything you'd like to practice? Oh, is that last part e to the 2x or e to the, oh, it wouldn't really matter. It's e to the 2x. So e to the 2x is 2e to the 2, derivative of e to the 2x is 2e to the 2x, just using the chain rule. But it would have worked for e to the 3x too. 2, 3, they're both eigenvalues for e to the, they're both eigenvalues for the derivative operator. Any number is an eigenvalue for the derivative operator. Are there any kinds of questions you'd like to practice?
Maybe we can like practice finding like eigenvalues and eigenvectors.
Let's do that. Okay, if I just write down an arbitrary matrix, the computations are going to get horrible. So let me find a matrix that will work relatively easily. Actually, I can make this work. How about we do this matrix? Find, let me see, let's let A be, how about 2, 1, 1, 1, 2, 1, 1, 1, 2. Find all eigenvalues. For each eigenvalue, find a basis for the eigenspace. Okay, so let's start with the eigenvalues. We're going to have to get the characteristic polynomial fired up. So we will take the determinant of A minus lambda times the identity. So that's just going to be the same matrix A. We'll take the determinant of the same matrix A with a minus lambda on each diagonal entry. So 2 minus lambda, 1, 1, 1, 2 minus lambda, 1, 1, 1, 2 minus lambda. So we're just taking the same matrix A and subtracting off lambda times the identity. The identity just has ones on the diagonal. The lambda times the identity just has lambdas on the diagonal. We just take a minus lambda and stick it next to each diagonal entry. Now we have to take the determinant of that. I'm going to do I'll do a cofactor expansion down the first column. So I'll start off with 2 minus lambda times. Now I'm going to cover up the row in the column that 2 minus lambda is in. I'm going to take this times this minus that times that. 2 minus lambda times 2 minus lambda, 2 minus lambda, minus 1 times 1. So that's this entry minus times its cofactor, the determinant of its cofactor. That times that minus that times that. Minus this entry, 1, cover up that column, cover up this row. So 1 times 2 minus lambda minus 1 times 1. plus this entry, 1, cover up this column, cover up this row, 1 times 1 minus 1 times 2 minus lambda. And it just fits. Oops, forgot to put this 2 minus lambda in parentheses. That was bad of me. Okay.
Wait. What did you just do? I glanced away for a sec.
Oh, I forgot to put this in parentheses.
Oh, okay. Whew.
Okay. So, all right, here we go. 2 minus lambda. This is just unpleasant algebra. Or maybe it's pleasant. I don't know. Maybe you like it. So let's FOIL this out. So lambda times lambda is lambda squared. Minus 2 lambda minus 2 lambda. That's minus 4 lambda. Plus 4. Minus 1. Minus 1 times, so I don't even have to write the 1 times. 2 minus lambda. Minus 1. Plus 1 times, I'm not going to write the 1 times. So 1 minus, so that, we'll distribute that minus sign in, minus 2, minus times minus is plus lambda. So 2 minus lambda times lambda squared minus 4 lambda plus 3. Let's see, 2 minus 1 is, let me put an extra line here. So that's just 1 minus lambda. And what we have here is 1 minus 2, that's negative 1 plus lambda. Let's see, minus 1. Okay, still going. Okay, now we're going to have to multiply all this out. So this is unpleasant, but this is just algebra. So minus lambda times lambda squared is minus lambda cubed. Minus 4 lambda times minus lambda is plus 4 lambda. Plus 4 lambda squared. Plus 2 lambda squared is plus 6 lambda squared. Let's see. Minus 3 lambda minus 8 lambda is minus 11 lambda. 2 times 3 is 6. Minus 1 plus lambda, after I bring that minus sign in. Minus 1 plus lambda. And now let's just collect up like terms. I guess I don't need this parenthesis anymore. Minus lambda cubed plus 6 lambda squared. Let's see, minus 11 lambda, minus 10 lambda, minus 9 lambda, minus 9 lambda, plus 6, plus 5, plus 4, so plus 4. And we're going to have to set that equal to 0. So we just took the determinant of A minus lambda times the identity, and we're going to set it equal to 0. Hang on for just a second. Okay. So now we're going to have to factor that. Okay, so let's see. We can try we have this, we set it equal to 0. I'm gonna multiply both sides by -1. So I'll have lambda cubed minus 6 lambda squared plus 9 lambda minus 4 equals 0. I'm used to seeing a 1 in front of the leading coefficient. So let's see if we can find a number. Can you find any solution to this? Any numbers that work easily? Here's an easy one.
I think 1 works.
1 works just fine, yeah. So that means that this is, since lambda equals 1 works, that means that lambda minus 1 is a factor. Let's see what the other factor is. Now we're using our pre-calculus stuff. To find the other factor, let's just divide. So lambda minus 1 goes into lambda cubed minus 6 lambda squared plus 9 lambda minus 4. So lambda goes into lambda cubed, lambda squared times lambda squared times lambda is lambda cubed, lambda squared times minus 1 is minus lambda squared, and subtract. Lambda cubed minus lambda cubed, they cancel out. Minus 6 lambda squared minus minus is plus. Plus lambda squared is minus 5 lambda squared. Bring down your minus 9 lambda, or plus 9 lambda. Lambda goes into minus 5 lambda squared minus 5 lambda times. Minus 5 lambda times lambda is minus 5 lambda squared. Minus 5 lambda times -1 is plus 5 lambda. Subtract. 9 lambda minus 5 lambda is 4 lambda. Bring down your minus 4. Lambda goes into 4 lambda 4 times. 4 times lambda is 4 lambda. 4 times minus 1 is minus 4. Subtract, you get 0 down there. So this is lambda squared minus 5 lambda plus 4. And then that factors nicely. Lambda squared minus 5 lambda plus 4 factors as lambda minus 1 times lambda lambda minus 4. Yeah. And so I have two different eigenvalues, lambda equals 1 and lambda equals 4. Notice what made this difficult is that we had to solve a cubic equation because I gave you a 3 by 3 matrix. Let me just say, to simplify things on the midterm, if you have to solve a 3 by 3 matrix, you can go ahead and use, Wolfram Alpha or something to solve that. I don't know if it's all that helpful right now to go back to your pre-calculus and do it by hand. It might have been a while since you did that. But you take the derivative of a minus lambda times the identity, set it equal to 0, and solve. So we've solved it. Lambda equals 1 and lambda equals 4. The answer to A lambda equals 1, and lambda equals 4. Let's find a basis for each eigenspace. So if we take, let's do lambda equals 1 first. So we want to solve a minus 1 times the identity times x equals the 0 vector. Lambda equals 1, that just goes in there. Okay, so let's just take A and subtract off 1 times the identity. So that's just going to be 2, 1, 1, 1, 2, 1, 1, 1, 2, minus 1 times 1, 0, 0, 0, 1, 0, 0, 0, 1. And that gives us the matrix 1, 1, 1, 1, 1, 1, 1, 1, 1. And so I want to solve 1, 1, 1, 1, 1, 1, 1, 1, 1 times x1, x2, x3 equals 0, 0, 0. And we know how to do that. We'll just write that, excuse me, we'll just write that as a augmented matrix, 1, 1, 1, vertical bar, 0, 1, 1, 1, vertical bar, 0, 1, 1, 1, vertical bar, 0. And let's row reduce that. I'm going to stop and wait till you catch up. Row 2 minus row 1. 1 minus 1 is 0. 1 minus 1 is 0. 1 minus 1 is 0. And 0 minus 0 is 0. And row 3 minus row 1. 1 minus 1 is 0. 1 minus 1 is 0. 1 minus 1 is 0. 0 minus 0 is 0. And that is in reduced echelon form. That didn't take very long. And so we have the first row says x1 plus x2 plus x3 equals 0. In other words, x1 equals minus x2 minus x3, getting the x1 by itself. And x2 is free. And x3 is free. No pivot positions there. There's only one pivot position. Only one leading entry. And so we'll just come up with variables for x2 and x3, parameters. x2 can be s, x3 can be t. And so x1 is equal to minus s minus t. And so x1, x2, x3 is equal to minus S minus T, ST. Put all the S's in one and all the T's in the other. So minus S, S0 plus minus T, 0T. In other words, S times minus 1, 1, 0 plus T times minus 1, 0, 1. And here is my basis for my eigenspace. So my basis is going to be minus 1, 1, 0 and minus 1, 0, 1. Comma. That's my basis for the eigenspace with lambda equals 1. Now for lambda equals 4, so for lambda equals 4, we'll take this matrix and subtract out 4 times the identity. So if I take this matrix and subtract off 4s in the diagonal and 0s everywhere else, I end up with minus 2, 1, 1, 1, minus 2, 1, 1, 1, minus 2. All I did is I took the original matrix and subtracted off 4 from each entry on the diagonal, which is 4 times the identity. In this one, I want to solve this matrix times x1, x2, x3 equals 0. So let's just write that as an augmented matrix. Minus 2, 1, 1, 1, minus 2, 1, 1, 1, minus 2, vertical bar, 0, 0, 0. There's a variety of ways you could solve that. I want a 1 in the upper left-hand corner. I could either multiply the first column by minus 1/2, or I could switch, sorry, the first row by minus 1/2, or I could switch 2 rows. I think I'm going to switch 2 rows. So I'll just switch the first and the second. 1, minus 2, 1, 0, minus 2, 1, 1, 0, and then 1, 1, minus 2. Now I have a 1 in that upper left-hand corner. I want to get zeros below it. So I will take row 2 and add 2 times row 1. Minus 2 plus 2 is 0. 1 plus 2 times minus 2 is 1 minus 4, that's negative 3. 1 plus 2 times 1 is 3. 0 plus 2 times 0 is 0. And I want a 0 there, so I will take row 3 and subtract off row 1. 1 minus 1 is 0. 1 minus negative 2 is 1 plus 2, that's 3. Minus 2 minus 1 is negative 3. 0. Now I want a 1 there. So I can take minus 1/3 of row 2, and minus 1/3 of 0 is 0, minus 1/3 times minus 3 is 1, minus 1/3 times 3 is -1. And we'll leave the third one alone for now. 0, 3, minus 3, 0. Getting there. Let's see, I want a 0 below that leading one now. I see I have a pivot position there, a pivot position there so far. So I'm going to take 1 minus 2, 1, 0, 0, 1, minus 1, 0. And I will take row 3 and subtract off 3 times row 2. And that gives me 0, 0, 0. Almost finished. I just need to get a 0 up here. So to do that, I will take row 1 and add 2 row 2s. So 1 plus 0 is 1, minus 2 plus 2 times 1 is 0, 1 plus 2 times -1 is -1, 0 plus 2 times 0 is 0. The rest of the rows stay the same, 0, 1, -1, 0, 0, 0, 0, 0. Now let's just jump back up to the top of the board over here. So what this says is x1 minus x3 equals 0. And this says x2 minus x3 equals 0. And of course, x3 is free. So, in other words, x1 equals x3, bring in the x3 on the other side, x2 equals x3, x3 free. And we'll just come up with a parameter for each of our free variables. This time we have 1. So let's just let x3 be st, I don't care, t. x1 is the same as that, and x2 is the same as that. So that tells me that x1, x2, x3 is t, or t times 1, 1, 1. And so here's my basis. So this is the basis for lambda equals 4, and this is the basis, the eigenspace for lambda equals 1. That was a lot of work. What was the most work there, I think, was just solving that cubic polynomial. The rest of it is sort of old hand for us. And looks like we're just about out of time. So I think probably what I'll do in the interest of keeping the computations on the midterm from getting too yucky is probably when we're computing eigenvalues, I'll probably stick to 2 by 2 matrices. That way I just have to solve quadratic, and that's easy to do. How's that sound? Okay. Unless you have any other questions, I will see some of you in 10 minutes. I will see some of you on Monday. Again, I will be posting the exam this afternoon. It will stay up until Wednesday. It's due Wednesday. Hopefully sometime between now and Wednesday you have some free time. It will be closed book, closed notes once you start the exam, of course. You may ask me if you have any questions, and you'll have like an hour and a quarter to do it. And in the interest of keeping it to an hour and a quarter, I will try to keep the computations reasonably simple. Is good? All right. Bye.